Well, it's time for me to try and show you a few of the exercises for linear and quadratic equations. So here are some linear and quadratic equation exercises explained. So let's just get right into it and start off with the first example here. First example, as always, these are equations, so we'll be solving for x. And here is the equation. X plus 7 times x minus 1 equals x plus 1 squared. All right. Now on the surface, this appears to be a quadratic equation. It is a quadratic equation right now. But as it turns out, with a little bit of effort, we'll see that it really reduces to a linear equation. So the first thing I'm going to do, there are no constants, no fractions to get rid of. There's really only one choice. Multiply out both sides. So multiply out both sides. Well, on the left, this is a pair of binomials, and we've multiplied many of those before. But recall, we multiply the x here times the two elements, the two pieces in the second binomial, and we get x squared minus x. And then the 7 times x and the 7 times minus 1. So we get plus 7x minus 7. And x plus 1 squared, of course, we've seen that before in the form x plus a squared. So I hope you remember that this is x squared plus 2x plus 1. Okay, having that done, now you see x squared appears only once there and only once on this side. And of course, I can subtract that from both sides, and it is gone. So this becomes, although it appeared to be quadratic, it becomes linear. So let's start simplifying some things. The minus x and the 7x is 6x minus 7 equals 2x plus 1. And then I'll bring the 2x over to here by subtracting. And then I'll bring the minus 7 over to the other side by adding. And I will have 4x is equal to 8. And taking this to the other page, 4x equals 8 becomes, of course, x equals 2. And that's easy, and I'll leave the check to you. So the moral of that is that things that look quadratic at first may turn out to be linear, so make a little effort to see what happens. Now I want to pose something to you, because this is the kind of thing that can happen when you're working with equations. There's a mistake here. I think you'll see why. Here's something, and I've written what's wrong up there. You start with x equals 2. And then by a series of manipulations, you end up with 1 equals 0. Now something's wrong here. Okay? 1 is not equal to 0, so there is a problem here. I will pose to you the question, what is the problem? So we'll leave this on the screen for just a beat, so you can look it over. And then when we come back, I'll show you where the problem is. Well, here we are back. Did you find the mistake? Well, let me show you exactly where it occurs. It occurs in going from this line down to this line. And the error is, whoever worked this out saw x minus 2 here and x minus 2 here and divided both sides by x minus 2, which seems like a legitimate operation, leaving x plus 5 equals x plus 4, and then leading to this conclusion, which is a contradiction. Now, why would that be a problem? Well, x minus 2 is 0. Why? Because we started out with x being 2. So x minus 2 is 0, and you can't divide by 0. That's an undefined operation. So there's the problem. Now, how could someone have avoided this error? Well, let me show you what one might have done, starting with this place up here, how one might have passed by that error. So here is the corrected argument. And the line I said was the place where the mistake occurred is x minus 2 times x plus 5 equals x minus 2 times x plus 4. All right, the mistake is to divide by x minus 2 because x minus 2 is 0 and that can't be done. However, if a student had not attempted that and instead brought everything over to the left, x minus 2 times x plus 5 minus x minus 2 times x plus 4 equals 0. And you should recognize this as that f of x equals 0 form I've talked about before. And now factor out the x minus 2, which is common. I have x plus 5 here minus the x plus 4 here equals 0. So that's x minus 2. X plus 5 minus x makes the x's go away. 5 minus 4 gives me 1. So I have x minus 2 times 1 is 0. And of course, the only solution to that is x equals 2, which is what we started with. So there is no problem here. There's no contradiction. And really, putting it in this f of x equals 0 form was the key to avoiding that mistake. So this is just a little piece of advice that I wanted to point out to you. Now let's go ahead and look at a problem a little more directly related to what we're doing. Here's a quadratic equation. Pi x squared minus x minus pi equals 0. Solve for x. I'll be back. All right, here's a solution to this. And this is the algebraic solution. This is a quadratic, as I recommended. I'm going to look at b squared minus 4ac first. So that in this case is minus 1 squared minus 4 times pi times minus pi. You should be very careful with your negative signs. So what does this become? This becomes 1 plus 4 pi squared. Now that's clearly greater than 0 because everything there is positive. And so automatically I know that I have two real roots and they are distinct. So that means I can go right to the quadratic formula because I was asked for the solutions after all. Minus b plus or minus the square root of b squared minus 4ac all over 2a, which becomes here minus b becomes, a minus 1 becomes plus 1. Plus or minus the square root, we've calculated what goes underneath there, 1 plus 4 pi squared, that's why I did that above. And 2a is just 2 pi. Now there's no more simplification I can do here, and so what I will do is approximate the two different roots I get out of this. So in the first case, this is approximately 1.17, and that's if I take the plus of the plus or minus, or approximately taking the minus of the plus or minus, minus 0.85. So there are my two approximated roots. The exact ones are here if I wanted to split them up that way. And if you want, you can go ahead and check this graphically. I will leave that to you. And also you can check that these answers actually work. Of course, if you use the approximations, expect only an approximate equation above when you finish. But you can check each one of those on your own if you like. All right, let's try another one. Now, this one is a little bit trickier looking. This is not a quadratic or linear as it stands. 9 plus 3 over x minus 2 over x squared equals 0. And I am telling you that x is not 0, so you can eliminate that from its domain. All right, try this one. Here we are. Let's look at the solution to this one. Now, as I said, this is not quadratic or linear. In fact, it's a rational equation. So the first thing I'm going to do is multiply by, let's see, what do I need? I have x squared and x on the bottom, so I will multiply by x squared. Now, I know that that's going to be fine when I cancel because I've already said that x cannot be 0, so I won't have any division by 0 turning up. So if I do that, I have x squared times 9 plus 3 over x minus 2 over x squared equals x squared times 0. While on the left, it will multiply out the fractions just the way I want it to. I'll have 9x squared plus 3x minus 2. And on the right, of course, I'll have 0. And now, finally, this is quadratic. So now I can use all the information I have about how to solve quadratic equations. So very often a problem that starts out looking non-quadratic will turn out to be quadratic with a little bit of work. Okay, continuing this, the first thing, as I recommended, was to look at b squared minus 4ac, the discriminant. In this case, that is 3 squared minus 4 times 9 times a minus 2. That's 9 plus 72, which is 81. And just for the record, that's greater than 0, so I know automatically I have 2 distinct real roots. Then I can go directly to the quadratic formula. Minus b plus or minus the square root of b squared minus 4ac all over 2a. Substituting in, the b is 3, so I have minus 3 plus or minus the square root of 81. That's from the work I did above. The a here is 9, so 2 times 9 is 18. Then minus 3 plus or minus the square root of 81 is 9 all over 18. And then from there, well, let's see, I'm going to have 2 possible solutions. I will have first equals will be minus 3 plus 9 over 18, and that will simplify to 6 over 18, which simplifies further to 1/3. Or I will have minus 3 minus 9 over 18, which simplifies to minus 12 over 18, and further to minus 2/3. So there are the 2, in this case, real roots or solutions to the quadratic we started with. I leave the check and the graph to you. You can now check these on your own. But that was how the calculation proceeds and how I recommend you attack these sorts of problems. All right, one final problem I want to pose in this section on exercises. It's going to take a little bit more out of you, so you'll have to think a bit. It does reproduce some of the things we've done previously, but you'll have to give a little bit of thought to things. Here's the problem. Solve for x. 1 over x minus a plus 1 over x plus a equals 2 over x minus 1, where a is some real number, unknown to you. Further, are there any constant values of a forbidden? Meaning, if you choose a to be some number, will there be no solution here? Will it causes this to be division by 0, for example, or something else? So you have 2 questions here. Solve for x. You'll find x is equal to something. And then answer the question, are there any values of a forbidden? And once you've solved the first part, the second part you'll see how to do. So go ahead and try that, and I'll be back. Let's begin with the solution. The first thing I want to note here is because this is a rational equation, I need to check and see where the denominators might be 0 and eliminate those cases. So the domain of x is the variable I'm interested in here, is going to be the set of x's in the real numbers, of course. This is my set builder notation again, such that x can't be a for the first fraction, so x is not equal to a. It can't be minus a for the second one, and for the third one it can't be 1. So x can't be a, minus a, or 1. And the reason is that all of those cause, up here, division by 0. Okay, with that in mind, let's go ahead and we'll do what we always do. We'll clear fractions. And we'll do that by multiplying by, well, let's see what we had here. We have these 3 denominators, so we should multiply by the product of them, which is x minus a times x plus a times x minus 1. Okay. Well, doing that, we have x minus a times x plus a times x minus 1 times the left-hand side, which was 1 over x minus a plus 1 over x plus a. Now that equals the right-hand side, which is multiplied by x minus a, x plus a, x minus 1. And the right-hand side was a single fraction, 2 over x minus 1. Then by multiplying through this triple product times the first one, we see that the x minus a's will cancel, leaving us with x plus a times x minus 1, plus, moving on to the second fraction, the triple times that, the x plus a's will cancel. We'll have x minus a times x minus 1. And that will equal on the other side, only the x minus 1 cancels. So I have x minus a times x plus a times 2. Okay. Well, what I want to do next with both of these sides, it's clear that I need to multiply things out. So I will multiply everything here on the left and then on the right also. And I'll slide those up here at the top and see what it is I need to do. X plus a times x minus 1. If you multiply that out, you have x squared minus x plus ax minus a, plus the other one was to multiply x minus a times x minus 1. And I'm assuming you've already worked on this. You can compare this with your own work. X squared minus x minus ax plus a. Now that's the left-hand side. The right-hand side, we had x minus a times x plus a, but that leads to the difference of two squares, if you remember. So that would be 2 times x squared minus a squared. I just put the 2 out front. Well, now let's combine things here on the left. I have 2x squared, so that'll be 2x squared. I have minus x minus 2x. The ax and the minus ax thankfully cancel. So I have 2x squared minus 2x. Also, the minus a and the a cancel. So I just have that on the left, and on the right I'll multiply this out. 2x squared minus 2a squared. Okay. Well, now I notice that the only x squareds that occur are there, and they are identical. I can subtract them from both sides. So actually this turns out to be a linear equation. Minus 2x equals minus 2a squared. Might even note that over here. This has turned out to be linear at this point. Well, I divide both sides by minus 2, and I end up with x is equal to a squared. And that is the solution. And recall, the domain said that x could not be a, minus a, or 1. So that is the solution. The check I will leave to you. But that's the solution, x in terms of a. That answers the first part of the question. What are the solutions? Solve for x, x equals a squared, where a is that arbitrary constant. Now the question is, are there any values of a that are forbidden? Well, let's see. X must be a squared, but x cannot be any of these things. So let us find out if we can answer the second question. Any a values forbidden? That was the question. Well, since, let me write out what I had on the previous page, since x equals a squared is the solution, and it must also be true that x is not equal to a, minus a, or 1, we do not want the following things to happen, and then we'll see what they lead to, and then we can eliminate them. We do not want a squared to be equal to a, because x is a squared, but it can't be a. We do not want a squared to be equal to minus a. Again, x is a squared, but it can't be minus a. And finally, we do not want a squared to be equal to 1. So let's solve these and see what a's would satisfy these, and then we can eliminate them. A squared equals a. Now, we'll put everything over on the left, remembering our lesson from before. Since we don't know what a is, we can't divide by a. It might be 0. A squared minus a is 0, and then a we can factor out, and we have a minus 1 is 0. So that means there are two solutions here. Either a is 0 for the first factor, or a is equal to 1 for the second factor. So these are numbers we will want to eliminate because they cause a squared to be equal to a. Over here we can do a similar argument. A squared plus a is equal to 0. So that's a times a plus 1 is equal to 0. And so that's a equals 0 for the first factor, or a equals minus 1. So we've gained a new number here, the minus 1 that we don't want a to be, because either one of these would cause a squared to be minus a. And finally, a squared equal 1. Well, this is of the form, if you recall, put it in a box here, we had box squared equals 1. Well, the solution to that was box equals plus or minus the square root of 1. That was our early quadratic solution. So doing that here, that gives me a is equal to plus or minus, well, the square root of 1 is just 1. So a equal plus or minus 1. That's another set of values we do not want. So what do we conclude from this? So x equal a squared is a solution provided a was not originally 0, 1, or minus 1, because that takes into account 0, 1, 0, minus 1, plus or minus 1. So the original problem, let me bring it back so we don't forget what we were doing. Here's the original problem. 1 over x minus a plus 1 over x plus a equal 2 over x minus 1. This has a solution whenever x is equal to a squared, but a is not equal to 0, 1, or minus 1. So we've answered the question with a little bit of effort, and it is an interesting problem to end off this section with. So then we'll come back and we'll look at some mathematical models.